Hello, White House Heritage Elementary. My name is Hazmat, and I'm with Mr. Bond and the Science Guys. And today, we're going to be doing some fantastic experiments together. But I thought, you know what? Let's start with the magic trick. Science is amazing a lot of the times, and a lot of the times it seems like magic, but in my opinion, science is much better because we do get to learn things at the end of all of those amazing things. So I thought, let's start today with that classic trick where you put the ball underneath the 3 cups and you move it around really fast. Raise your hand if you've seen that. Great. Except for the first thing about this I have to tell you is the science version is going to be a little bit different. This time we're going to put water in the cup. And if you can guess where the water is, I will pour it on my head. Now I know what you're thinking. Maybe that's not real water, but no, check it out. It's just regular everyday water. And I'm going to pour it into one of these cups. By the way, this is cup number 1. Everybody hold up 1 finger. Cup number 2, hold up 2 fingers. And cup number 3, hold up 3 fingers. If you want to show me where it is, just show me with your fingers, okay? Just to be sure you're all paying attention. Which cup is the water in? 1, 2, or 3? 1, perfect. Now watch closely because I will fool you. All right, on your marks, get set, go. Now you have no idea where the water is. You're all saying 2. You want me to pour 2 on my head? Well, you know what I was just thinking? That was just practice. That didn't count. That didn't count. I'm not going to pour that one on my head. Let's see if you're right. And yeah, you're all pretty good guessers already. I can tell. It's because we have the 5th graders with this. All right, let's try it again. On your marks, get set, go. Now you have no idea where the water is, and you're all saying 2 of it. You know, everybody needs a second warm up. That didn't count. That didn't count. Let's see if you're right. And yeah, I think I'm definitely getting wet today. All right, last time. Here we go. On your marks, get set, go. Now you have no idea where the water is, and you're all saying 2 of them. Great, fantastic. Okay, that's fine. I said I'd do it. I'll take number 2 and I'll pour it on my head. You're saying that's not number 2. Oh, okay. All right. I'll take number 2 and I'll pour it on my head. That's not a problem. I don't mind it. You're all saying that's number 2. This is the one you want me to pour on my head. Huh? Okay. All right. I'll do it. I guess I said I would, right? Here we go. 3, 2, 1. Did I tell you I was going to fool you? Clearly, we don't have to look at the other cups, right? We do have to look at the other cups. This one I could pour on my hand, though, right? No, you're all saying pour it on the head. Okay, we'll try it. We'll pour it on the head. 3, 2, 1. No, we don't have to look in that other cup. I know what you're thinking, but we don't even need to look in there because, yes, we do need to look in there. You're serious about this. I can tell you're serious. On the hand? Got it. Okay. All right. Here we go. Last one. I think maybe I'm going to get wet. Here we go. 3, 2, 1. Wait, what's that? Hold on. Wait a minute. Did it disappear? Did I make it evaporate? Now, if this was a magic show, which it is not, I would just say, ta-da, and that would be it. It would be done. But no, this is science. We're here to learn things, right? Now, would you believe me if I told you the water is still in the cup? I actually never took it out. That's right. The water is still in the cup. And all I actually had to do for this magic trick was put a special powder in there that soaked up the liquid. And if you're thinking to yourselves, I bet you that's sodium polyacrylate. You're right. Very smart kids. Let's see what sodium polyacrylate mixed with water looks like. Ah, perfect. What does that look like to you from the audience? Maybe ice or snow. Now, it does look like ice or snow, but I must tell you something. It's kind of warm and it's kind of squishy. So there's probably no ice and snow out there that could actually be turned warm and squishy. We actually do use this as fake ice and snow in the movies, but that's not why this was invented. This is actually the stuff that you find in diapers. Okay, I can see some of your faces. Not that stuff. No, this is the stuff that absorbs the liquid in the diapers. Never mind. All right. So anyway, you might be saying, well, Hazmat, what do diapers have to do with science? And believe it or not, great scientists actually worked on diapers, and actually for a pretty cool reason. Raise your hand if you've ever heard of NASA. See, NASA is a place where great scientists shoot rockets up into space and even people up into space. And it turns out, you've probably seen their big spacesuits, right? Well, it takes about an hour to take those off. And then if you want to put it on, it takes another hour or so to put it back on. So if you're out there in space walking around and you need to go to the bathroom, all of a sudden you've kind of lost 2 hours where you could be out in space. So NASA decided to themselves, well, what if we can just invent something where you can just go to the bathroom in your spacesuit? And that's why diapers were invented. And now you all use them every day. I mean, your parents, we all, never mind. Okay, moving along. Yeah, so I'm actually, unlike our fake snow, I've actually been making some real snow as we've been speaking right now. And of course, to make real snow, it's not very complicated. All you need is water and something cold, right? Everybody breathe in and breathe out. What did you breathe in? I mean, yeah, you could say air, but there's oxygen there. Air is mostly nitrogen. And believe it or not, there's actually water vapor just hanging out in every room, even the room that you're in right now. So we are going to do an experiment right now where I actually make some real snow by just putting something super, super cold inside of the room. Now, this is called dry ice. Everybody say dry ice. And it's dry because, well, it never melts into a liquid. It only goes from a solid into a, what? What is this? A gas. Perfect. It turns into a gas. And it's actually so cold that if I hold it without wearing a glove, it can give me frostbite. So you'll never see me grab it without a glove. But it's also so cold that it's taking some of that water out of the air and condensing it down into real snow. Maybe like what you thought I did before with the magic trick. And actually, I'm going to make the world's smallest little blizzard on my black glove so you guys can see it. Here we go. 3, 2, 1. Ah, real snow. Taken from the water out of the air inside the room, condensed onto my super cold ice. Pretty cool, right? Like literally, like 109 degrees below zero cool. Now, because this is ice and it's really, really cold and it turns into a gas, we can actually do some pretty interesting experiments. Experiments that you definitely couldn't do with just regular everyday ice. We're going to do an experiment where I actually can make a pan sing just by touching ice to it. Would you guys like to hear the song? All right. When you hear it, you can raise your hand and even sing along if you know the song. Here we go. 3, 2. Okay. All right. It sometimes does this. Let's try again. Here we go. 3, 2. Ah! Okay. That's too awful. I won't do it again. I guess it's not making a very good song. And I have a feeling that you don't like this music very much either. I think I know why. Do you know what this music is called? This music is actually called heavy metal. Never mind. Anyway, so it's not making a song, fair enough, but it is making a vibration. Everybody say vibration. Vibration, right? So it's taking, and remember, this is turning from a solid into a what? A gas, right? And when it does turn into a gas, it heats up and it pushes the pan away. And then, of course, I'm pushing the pan back with my hand, and it goes back and forth and back and forth and back and forth until it makes a vibration. Every time you have a vibration, a quick moving, something that moves really fast, you have a sound. Everybody hold up your hand like this. Move it around. Faster. Faster. Okay, you can stop. You just made a vibration, right? You moved something really fast, but did you make a sound? You don't hear it necessarily right away, but if you do it next to your ear, you should hear that you are making a sound. You're taking and you're moving the air in waves. Sound travels in waves once we make a vibration. So when I talk, my sound travels in a wave through the air and it hits my microphone right up here. That sound then travels with electricity all the way to where you are, and it actually moves the air in your room when it comes out of the speakers. So just by touching my ice with my pan, I can make that sound travel and make you cover your ears. Pretty cool. Now, that's one way to make it vibrate, but scientists like to look at different items and say, well, that pan is made of metal. This quarter is made of metal. I wonder what would happen if we put the quarter in. Scientists might think something similar. If you think it's going to vibrate, you might be just right. Let's see if it does vibrate. Here we go. Quarter inside of the ice, and ooh, you might have noticed a little bit of gas flying up, and that's pretty cool, right? So what happens is the quarter is a lot hotter relative to the ice. So when the quarter touches the ice, it turns it into not a liquid, but a gas. It makes it hotter, and that gas comes off and pushes the quarter back and forth and back and forth and back and forth and back and forth. And it makes a different kind of sound. I'll try to hold it next to the the microphone so you can hear it. That's one kind of sound. All sorts of different vibrations are going to make different sounds. Not everyone hurts your ears, like the inside of the pan. That kind of thing. Excuse me. All sorts of different vibrations make different sounds. So we're going to notice that a little bit, but the most important thing to know is that it has to have air to travel. If you shout out in outer space, nobody's ever going to hear you. So that's kind of interesting. Now, let's explore this a little bit further. This dry ice stuff turning from a solid into a gas, never melting. What else could we do with it? Well, let's go ahead and put a little bit into our flask here. If I want to turn this ice into a gas, what do I need to do? Make it colder? Probably not. We need to make it hotter. Normally, that's called evaporation when something goes from a liquid to a gas. But when it's a solid to a gas, it's got another name altogether. It's called sublimation. Everybody say sublimation, sublimation. And it's sublimating when it gets hotter. Now let's go ahead and add some water, and you might notice a change. There's a lot of gas stored up in there, and just by adding that hot water, we can see just how much gas is trapped inside. And perfect. Immediately, none of that ice has gone away, but we have a lot of gas coming out. And that's really pretty to look at. Now, this is a special kind of gas that comes into our life a lot of the time. And it's beautiful to look at, sure. But we have other senses as scientists. Of course, we want to touch it and see what that feels like. And it doesn't feel much different than the air all around you, honestly. If you've ever felt just a little breeze, that's all I'm feeling right now. But we have other senses as well. Should I taste it? Never taste anything in science if you don't know what it is, of course. Should I smell it? Probably not. Probably shouldn't be smelling anything in science if you don't know what it is. But tell you what, I'll tell you about it, and we'll decide if it's safe together. Everybody, hold your breath. Keep holding it. You're doing great. Now, all of these bubbles here, you might notice, those are bubbles that we have drinking into our body before. It's called carbonation, right? Those are the carbonation bubbles in our sodas. Also, this gas is very important for putting out fires because it gets rid of oxygen a lot of the time. And that's another really important use. Also, this gas is outside. The trees breathe it in, give us back oxygen. Oh, wait, are you still holding your breath? Oh, yeah, you can let out now. And what you just breathed out is this gas. It's called carbon dioxide. Everybody say carbon dioxide. Now let's think about it. We drink it in our sodas, carbonation. We breathe it out. It's been in our lungs before. So what do you think? Safe to drink? Maybe. Pretty good. If you want to try, just open your mouth. Here you go. What's it taste like? Sprite, Coca-Cola, Mellow Yellow, Dr. Pepper, Root Beer, Fanta, Mr. Pibb, LaCroix, LaCroix, LaCroix. I don't know how to say that last one, but that's probably the one it tastes the most like. It tastes a little bit like soda water, if you ask me. Now, very, very cool stuff. And actually what you're seeing, though, is interesting. It's not actually the carbon dioxide gas. What you're seeing is the carbon dioxide gas grabbing a little bit of water vapor and pulling it up and making a real cloud inside of our bottle, mixed with carbon dioxide. So water vapor mixed with a little carbon dioxide. Now, that's pretty cool, but I think we can still go a little bit bigger. Everybody say bigger. Now, a little bit of our dry ice inside of our container here. And then I'm going to add some hot water. And then we need to make a bubbling potion. And to make our bubbling potion, I'll have to add some of our super secret ingredient over here. You probably have no idea what it is. No, you have no idea what it is. I don't want to hear anybody say they think they know what it is. Okay, yeah, if you said soap, you're right. And the only important thing is that you shouldn't add too much, because if you add too much, these things are never going to stop. Now, a little bit of soap bubbles is actually acting to catch all of that carbon dioxide gas and water vapor inside of each of these bubbles. But clearly, I think I've added a little too much, because now I have these bubbles, but it still just keeps coming out. We're sort of in a disaster area here. This might try to fill up the whole room. I'll put some under there for a minute. And yeah, it's still coming out. Everybody say bubble, bubble, toil and trouble. Okay, and not toilet trouble, just to be clear. Toilet trouble. Let me put a little bit in my pocket. I'll save that for later for my next show. A little bit over here. Everybody, high five. Perfect. Very cool. Ooh, nice. And this lab coat's a little dirty, so a little bit more under the arms. There we go. Perfect. All set up for later. Yeah, so bubbling potion just uses a little bit of soap and our sublimating carbon dioxide gas, turning from a solid to a gas is sublimating. Now, obviously, we can't just play with bubbles all day. Let's go ahead and put the lid on. I'll move these around over here. All right. Now, enough of that. Who wants to blow something up? That's what I thought. One other really fun experiment I'd love to do with our dry ice is put a little bit of this dry ice into a container and then seal it up. Who thinks that's a good idea? Generally not a good idea. Now, if you have a special container like I do, where the top comes off super easy, it can be a good idea because I know that this top is going to come off, but screw-on tops might be a really bad idea because then the container might explode before I'm ready. So let's add a little bit of hot water, and you might know that the gas starts to grow and expand and get bigger. And then what I'm going to do is put the top on. If I put the top on, what's going to happen? It may explode. So if it's not going off for some reason, should I ever point it at my face and say, why isn't this thing going off? You don't want to do that. So I'm going to go ahead and point it up, and actually safety first, everybody. I'm going to go ahead and wear my safety goggles just in case. And let's see how long it takes. Let's count down from 5, just as a guess. Here we go. 5, 4, 3, 2, 1, 0, -1, -2, -3, -4. Oh, Houston, I think we have a problem. I think there's a leak in my top. Let's try another one. Here we go. Here we go. 5, 4, 3, 2, 1. Oh, Houston, we have another problem. There's another leak in this top of this container. Sometimes, even if I check these right before, even if you check them right before the show, sometimes they have little leaks because this ice has a lot of pressure that builds up. Let's see if we can get it. 5, 4, 3, 2. That won't hit me in the head. Yeah, that was pretty good. 5, 4, 3, 2. How many seconds was that? It didn't go off on 0. 5, 4, 3, 2. 4 seconds, 3 seconds, something like that. Let's try it again. Let's count down from 3 this time. Here we go. 3, 2, 1, 0, -1, -2, -3, -4, -5. What the? Okay, so we just started out from 3, and we ended up at -5. How many seconds was that? Well, you just have to add the two numbers together. 5 plus 3. Then you got 8. Now let's try it from 8 this time. For sure, we'll land on 0 this time. 8, 7, 6, 5, 4, 3, 2, 1, 0, -1, -2, -3, -4, -5. It actually went a little bit longer that time. How many seconds was that? 8, and I think -5 is about where we landed. So if you add them together, what do you get? About 13 seconds. Now, if you're paying attention, why did it go longer every time? Did you notice, like, once we got the right lid on that didn't have a leak in it, it seemed to go a bit longer every time, didn't it? Anybody know why? Well, if you said that we lost a little bit of our dry ice gas, our carbon dioxide gas, every time we did the experiment, you're right. But another really interesting thing that happened is that as the ice sat in the water got colder, so there was less energy for our explosion. Now that's a pretty great explosion if you ask me, but I say we go bigger. Now this time, that's a rocket launcher. Bam. And I think we're going to need a little bit more fuel if we're going to go a little bit bigger like that. So let's go ahead and add a little bit more fuel. Let's go a piece that's 2 or 3 times as large as the last time, and then another 2 of those. So maybe 6 to 9 times larger. Is that going to be enough though? Say no, that's not enough. All right. That guy, whole thing. All right. Is that enough? You want more. All right. Let's go ahead and add a little bit more. That, is that enough? No. Okay, that, and that, and that. Okay, that's going to be enough. For sure. Okay, that's going to be enough. Now, that would be pretty cool just by itself if we put the cups on, but we want to make the energy. We want to take the solids, turn them into a gas, and make all of those molecules, the smallest parts that make up the gas, make all the molecules bounce around like crazy. So here's our heat, here's our energy, and now we have a fantastic rocket launcher. And all we have to do is high-five these cups down into our base, and we should be able to start our experiment. Now, as the pressure builds up, it's going to push the... Okay, so let's try again. As I was saying, I broke all my cups. All right, as I was saying, as the pressure builds up, it's good. Hold on one sec. They got to really kind of have a problem here. See, as the pressure, but I think we added too much gas, you guys. Didn't I say that was enough at 3? All right. Now, oh, hold on. We're going to make a giant explosion. It's going to happen for sure this time. Here we go. Now, as the pressure keeps going off. Hold on. I've got a different cup that I'd like to try for the very first time here with you today. Let's see how a paper cup works. My styrofoam cups keep getting kind of beat up, so let's see if I can get my paper cup. Oh. It'll work for sure this time. As the pressure builds, I give up. We can't do it anymore. But what would go higher? 10 cups, 5 cups, or 3 cups? Raise your hand if you say 10. Raise your hand if you say 5. Raise your hand if you say 3. Raise your hand if you say, I have no idea. I have no idea is honestly a pretty good science answer. Let's try 10. 10 cups. Okay, not very high for 10. I'll have to say that. Let's try 5. A little higher. Let's try 3. A little higher. Should we try 1? Maybe we shouldn't try 1. What if 1 goes through the ceiling? If you don't care. It's your lab. Why don't you just go for it? All right, 1 cup through the ceiling. Pretty good. But of course, it's never going to break through the ceiling. And it just doesn't have enough force because it's not very big. It doesn't have a lot of mass, so it can't have a lot of force. All right, now that's a certain type of pressure. That's high pressure. What would the opposite be? Low pressure. Now, low pressure would be like this. What if I took all of the air out of this room? What would happen? Other than the fact that we would die. What would happen to the air if I took all the air out of this room? What would the air outside want to do? It would want to rush in. Gas always wants to fill spaces where it is not. Now I'm going to take all of the air out of this jar, and we're going to create an environment kind of like outer space. You see, space doesn't have any air, and we call it a vacuum. Not like the vacuum that you use at home, but a vacuum where there is no air. Now you can see with our close-up camera what the jar looks like. Let's go ahead and take the air out of the jar and just watch and listen. Now that air is rushing out of the jar. What you might notice is you can't take the lid off once the air leaves because the air outside is trying to push its way in and it holds the whole container together. But nothing else too much is happening. We're used to not seeing air, so we don't notice when it leaves. Let's let the air back in. Now, if you listen closely, you did hear evidence of change. You might not have seen it, but you definitely heard the air rush back in, didn't you? Now, let's go ahead and try to put something into the vacuum chamber. What's going to happen with our ping pong ball? Raise your hand if you think it's going to float. That's a common answer. A lot of people say it's going to float because it's like in outer space where things float. If we take the air away, does that mean gravity goes away? Let's test it out. Also, lots of people say that they think it might explode. If you think it's going to explode, raise your hand. Okay, I didn't say who hopes it's going to explode. Let's go ahead and try it out. 3, 2, 1. The air is leaving the jar. I saw it roll a little bit, but it is not floating, and it's not exploding yet. Let's give it 3 more seconds or so. Okay, should I let the air back in? Here we go. 3, 2, 1. That was pretty cool, if you ask me. And nothing really happened when we took the air away. So gravity was still there, still holding it down, even though there was no air. It didn't explode. And that's partially because this has a pretty hard outer shell. It's going to be hard for the air inside to grow and expand to be big enough to make this explode. But when we let the air back in, what we did notice is that it blew it all around the whole vacuum chamber. So that was pretty cool. Now the ping pong ball is full of air, just like our balloon is. What happens if I put the balloon inside? What do you think? The balloon is full of air. The air inside of the balloon might try to fill up the whole container if there's no air to hold it down into place. Let's see if that does happen. So the gas always wants to fill every container that it's in if there's not as much air around it. Everything in nature wants to have equal amounts all over. So let's try it out. That's pretty cool. Okay, I think it's stopped. Now, what happens if I let the air back in, though? Should I try it? All right. 3, 2, 1. Oh, wait. 3, 2, 1. Ooh. Is that even what you thought was going to happen? When we took the air from outside of the balloon, all the air got bigger. But when we put the air back in, it just went back to its original shape and size. By the way, some of you might have thought it was going to pop, right? A lot of people say that. But even if it did pop, I wonder, would you hear it? If there's no air inside for the air to travel, for the sound to travel, would you hear it? Probably not. In space, if a balloon pops, there's nowhere for that sound to travel on the air, so you don't hear it. Now let's go a little bit further. Let's send our astronaut into outer space. Our astronaut, is he a solid, liquid, or a gas? Yeah, solid. It's a pretty simple question, but believe it or not, there's lots of pockets of gas, and that's why it's squishy. You can't really squish most solids like that. Like if you try to squish metal, it doesn't work. The reason it's squishy is because of the air pockets. So what happens if we put our astronaut into outer space? What should we name him? Marshy? Marshy? Marshy the astronaut? Marshy the Martian, of course. Yes, Marshy the Martian. Let's go ahead and put Marshy the Martian into outer space. What's going to happen to Marshy? He's full of air, a lot like the balloon, so I bet you can make your hypothesis, right? You have done your research, you've seen what balloons do with air, so you might know what the Martian is going to do since he's full of air. Let's go ahead and try it out. Here we go. 3, 2, 1. Okay, he's getting a little bit bigger. Sort of a Ghostbusters scenario we have on our hands. Wait, of course, he can't breathe. Should I let him breathe? No. What kind of people are you? Let's let him breathe. Here we go. 3, 2, 1. Marshy, I'm coming. Uh-oh. You guys, I think he's gonna be okay. I think he just got kind of like really old really fast or something. But look, I think he's gonna be fine. With a little bit of bed rest, he'll be just fine. So I wouldn't worry. I say he's gonna be just fine. Don't worry about Marshy. After a little bit of we're just gonna put him in the hospital over here. He's gonna be fine. Don't ask questions. Don't ask questions. All right. So unfortunately, that's about all the time we have for today. It was gonna be a pretty quick show, about 30 minutes. I hope you guys had lots of fun. And I hope you learned a lot. And ask your teachers about some of the stuff you saw today if you want to know a little bit more. I do have 3 questions for you guys before we go. Number 1, is science fun? Is science cool? And the last question, everybody, is science easy? Wait, you're saying no. You're saying no. Some of you are saying yes. You're all confused. Anyway, I hope you had lots of fun. Hopefully we'll get to see each other in person one day. And I really enjoyed hanging out with you guys today. And thank you so much for having us. Bye, everybody. See you later.